parameters pick up the pings and estimate the time of arrival. From the time of arrival of the pings to the different receivers that are sent to a server, the system can estimate the location of the tag and therefore the location of the animal. And you can see in the map on the right, you can see tracks of a young barn owl flying around night after night. Different colors represent different nights. The tags can be smaller. This is a very small tag attached to a reed warbler, to a songbird. There are also tags that are appropriate for bats. This is a small insect-eating bat. These tags have been used on even smaller bats. So that's the context in terms of the transmitters. In terms of the receivers, this is basically what a base station looks like. The base station or the receiver includes an antenna. Usually we try to put the antennas high up. This is an antenna on top of a cellular tower. Most of the antennas there are not the Atlas antennas, but the little line there on top is the Atlas antenna. There's also a low noise amplifier next to the antenna, then a long cable running down the tower, then a small adapter board that includes an RF filter and a mechanism to power the mask amplifier, and then the signal gets to a sampling receiver. The sampling receiver samples the RF spectrum and moves the samples to a computer, normal computer running Linux or Windows, that performs the signal processing that we're going to talk about in this talk. The role of this computer that performs the signal processing is to detect the pings and to estimate the time of arrival of the pings. And then this computer sends the time of arrival and the detection report to a server. Before we move on, I want to show you what this tracking looks like in real time. This is real time, but accelerated 100 times. This is the actual application that the users use to view where the animals are. These tracks are of a bunch of fruit-eating bats leaving an orchard at the end of the night. So this is what it looks like in real time, except it's much slower. It's a system that's used by ecologists. It provides them with unique tracking capability. This is demonstrated by high-impact papers that rely on this tracking data, on Atlas tracking data, like this recent paper that we published in Science just in July, and other papers and more that are forthcoming. There are systems in Israel, in the Netherlands, in Germany, in the UK, and ecologists are using them to study the behavior of animals. Before we move on to the signal processing part, I want to explain how the time of arrival estimates are transformed into location estimates, because the users care about locations, they don't care when the pings arrive. The relationship is driven by the relationship of the distance, is driven by the distance between the unknown location of the tag, which we represent by XY, and the known location of the receiver. We know the precise location, 2D, really 3D location of the receivers. The distance between them is just the Euclidean distance, and therefore the time of arrival represented by T1 equals the time of departure plus the propagation time. And the propagation time is this Euclidean distance divided by the speed of light. C is the speed of light, which is also the speed of propagation of radio signals. Now, one equation like this is not enough to estimate location, but when you have several equations like this, you can estimate locations. We add to each equation a noise or error term represented here by epsilon1, epsilon2, epsilon3. They're used to compensate for the fact that the estimated arrival times are estimated arrival times, not precise arrival times. Each equation corresponds to arrival time to one receiver. The different receivers have different locations. And from this system of equations, we solve for the unknown quantities, which are depicted in blue here, the time of transmission and the 2- or 3-dimensional location, XY or XYZ of the tag, the animal. using normal least squares minimization. We minimize the error terms or the residual, if you like, in a least square. This is non-linear least squares, but it's still a least squares problem. This is how the arrival times are transformed into locations. The quantities in blue are the quantities that we seek to estimate that we don't know. The quantities in red are the quantities that we know. We know the location of the base stations, the receivers, we know the speed of light, and we know the estimated measured arrival times. Okay, what the GPU tasks and CPU tasks, the signal processing tasks do is they detect the pings and they estimate the arrival times. To explain what they do, I want to first explain how they're scheduled. The base station software prepares and schedules signal processing tasks. And to explain what the tasks do, it helps to understand, again, the slightly larger context of the scheduling. This was perhaps difficult to understand or missing in the written paper. We got some very useful feedback on that. So here in the talk, we have an opportunity to explain that part of the context that was hard to explain. Also the details, we'll also explain the details of the signal processing. The tags ping periodically with a known period, which might be 1 second, once every second, once every 2 seconds, every 4 seconds, and so on. And here we see along the timeline pings by 3 tags that are represented by red, by orange squares, cyan squares or blue squares, and green squares. The orange tag transmits every second, let's say, so very often. The blue cyan one transmits every 2 seconds, so the offsets are the same within a second, but it transmits less frequently. The receives RF samples from the radio and places them into a circular buffer. The circular buffer can hold somewhere between 10 and 30 seconds worth of samples, and the signal processing tasks take samples from the buffer and process them. It's not real-time processing that processes samples as they come in, but it's near real-time processing that takes samples from a buffer, processes them. There are fewer real-time constraints this way. It simplifies the software and still provides near real-time performance. The scheduler has two queues: a tracking queue for the tags whose next transmission time is known, and a searching queue for tags that have not been heard in a while and we don't know when they're going to transmit next. Obviously, in the tracking queue, which here includes the blue, cyan, and the orange tag, the scheduler knows when the next unprocessed transmission time is, and it has a pointer to that time in real time, basically. The buffer is labeled with real time, with the real time of each sample. Okay, let's see how the scheduler operates. At every step, it needs to, after it finished processing a task, it needs to decide on the next task. And the first thing to decide is whether it's going to be tracking or searching. And it does this using amortization of the processing time. Let's assume that the next task is going to be searching. So while searching, we know what part, this part here in the timeline that's marked by searching is the next piece of RF that was not searched for the unknown tags. So the task is going to search this chunk of RF samples for the green, red, and purple tags. It's only going to find the green one because the other ones are not transmitting. Maybe they're in a cave, they're out of range. They're not detectable by this base station. Okay, so we do searching. How is the state going to change? We're going to detect the green tag, and that's also going to tell us when it's going to transmit next, because it transmits every 2 seconds. The green tag is going to move from the searching tag to the tracking tag, and the next chunk of RF to search for is going to move forward. So that's indeed what we see. The next chunk of RF to be searched for moves forward. There is an overlap designed to ensure that a transmission is always wholly contained within some searched window of RF samples, and we move the green tag from the searching queue to the tracking queue. Okay, what's going to happen next? Let's assume that tracking is going to happen next. Tracking is prioritized from oldest to newest because the cyclic buffer is moving. And you'll notice that the cyclic buffer has moved. Let me move back. You see that while we were searching, the cyclic buffer has moved. And that's because searching took time. During that time, the receiver placed more samples in the buffer, and then those samples overwrote the tail, the oldest part of the buffer. Therefore, when we are going to do tracking next, we're going to try to track the blue tag, but the tracking software is going to decide, or the scanner is going to discover that the relevant samples are no longer in the buffer. So it's going to try to do this tracking. It's not going to succeed. It's going to mark that, that's the X, as undetected. So it went undetected because we didn't do this on time. And it's going to move the next transmission time to process for the blue tag, the cyan tag, from the one that we just missed to the next one. Hopefully we'll get it. And then it will, if it stays in tracking, it will now track the orange tag, which is in the buffer, and it's going to discover it, detect it, we'll mark it with a check mark, and so on. So this is how processing, this is how the scheduler generate tasks. And what I want to emphasize here before moving to what the actual signal processing tasks actually do in terms of their math is to emphasize the fact that there are two types, tracking tasks and searching tasks. The tracking tasks process a small window of RF samples, typically about 12 milliseconds. That's the 8 milliseconds of the transmission plus margins of 2 milliseconds on either side. Searching tasks typically search 100 milliseconds, almost 10 times more RF samples, and they search for multiple tags, all the tags that we haven't heard from in a while. Tracking tags focus on a small window of RF in which we know one tag should be heard, and we search only for transmissions, or trying to detect only transmissions of that tag. So the two tasks are slightly different, and their performance is also slightly different. Okay, so what does the signal processing flow within a task looks like? The tasks, so here we depicted here on the left a chunk of this cyclic buffer. So that's a chunk that includes the samples in which the orange tag is transmitting or is being received. It's a complex signal. This is a complex vector. It's a complex signal in which the two components are represented by small integers. So the first time is an element-wise operation to transform that into a real floating point, 32-bit floating point complex vector. Once we do that, we transform that using an FFT. That's the second processing step. And we get the transform signal, the FFT of the original signal. Then we process it twice. It looks here like we duplicated it, but we actually don't duplicate. We use the same memory representation twice. The next phase of processing is multiplying it element-wise. The circle dot represents element-wise multiplication by transformed vectors of the same length. These vectors represent one bit, one symbol out of 8,000. It's padded, and that's part of a matched filter. Once we do this element-wise multiplication by two vectors, let me just move that. We transform these signals back, and then we perform element-wise operations, subtraction and divisions between the two vectors, between the two back transformed vectors, to produce a demodulated signal, a signal that tells us basically in a soft way, in a real way, whether the symbol that we see in each particular sample is a +1 or a -1, or a 1 or a 0, if you like. Then we perform a match filter to find the code, the unique pseudo-random code that the tag transmits, and that's done by performing an FFT again. This is a real to complex FFT, multiplying that transformed signal element-wise by a transformed code, the transformed bit sequence basically, which again is the same length, and then transforming back. Once you transform back, you get we get a cross correlation signal, a real cross correlation signal, and we do reduction operations, finding the maximum value, the elements near the maximum value, the norms, and so on, which is what the signal processing outputs. The yellow vectors that we multiply element-wise by are constant. They're specific to either the bit, which is the 2 bits, which are the same for all the tags, or the code, which is the same for the same tag over and over again, but we have many of them when we search, and these are stored in the memory of the CPU or the GPU. So what we have here is a bunch of operations, and all of them fall into very few categories. There are lots of FFTs. Some of them operate in batches because of the overlap add optimization, or because of multiple independent codes that we search for. There are element-wise operations. There are reductions. It says here at the end, but there are also reductions at the beginning to compute the maximum over the samples and so on, other norms. And then there are stored vectors that are always FFT, transformed vectors. We produce some time domain vectors, we transform them, and we store the FFT of the frequency domain vectors in the memory of the GPU or CPU in order to reuse them multiple times afterwards in element-wise multiplication. So that's basically what the signal processing within each task looks like. Sometimes here in this last part, there is just one code to correlate against. This is in tracking. In searching, there could be 100, 60, 100 different codes, transform codes that we correlate against in order to detect all the tags that we haven't heard from for a while. Okay, next we're going to see how these building blocks transform into CUDA code, host code, and so on, and Yaniv will do that. So Yaniv.
So most of you are probably familiar with CUDA, but I'll show here some basics so to make sure that the next slides are clear. So when we use CUDA, the CPU first allocates memory in the GPU, copies data to that memory, invokes a kernel, and finally copies the data back to the CPU memory. So the kernel is a GPU, it will run on the GPU, and it runs on several threads. The threads are grouped into blocks, and each thread are responsible for a single element in the data in the array. The number of threads and blocks depends on the GPU architecture and the size of the array of the data structure. So this is a basic element-wise kernel. It first computes the index of the element it should work on, and then invokes the operation. Our kernels are more complicated than this kernel, but only in details, but the structure is quite similar. Okay, so it's harder to optimize reductions, to write and optimize reductions, so we use the CUB. We use CUB block reductions, which computes the reduction for each block, returns the result to the first block, to the first thread of the block, and eventually we use atomic operations to get the overall result, to synchronize over all blocks. we use cub in this way, so we can mix element-wise kernels with reductions and optimize global memory access this way. Okay, so this is our demodulation code. It's the overall structure. It's not the exact code, but it's the demodulation code. The data parallel kernels are shown here in blue. They perform mostly element-wise operations, but also reductions like computing the power of the signals. To compute FFTs, we use CUFT, depicted here in green. It's NVIDIA's library. And as explained earlier, the algorithm uses pre-computed vectors shown here in red. Okay, so this is basically it with respect to how we implement the algorithm in CUDA. We have a lot of FFTs, so we use CUFT for them. Our kernels are mostly element-wise, simple kernels, but they use kube for reductions. Our code is more complicated than what we've seen here, but only in the details. And the real code, the code itself can be is available freely, and you can see. Okay, so the code was originally optimized for a single core CPU, but we used mostly the same optimization for the CUDA code. For example, the use of high performance FFT libraries. We aggressively reuse allocated arrays on we allocate them on the GPU, of course, and reuse them. We pre-compute anything that we can in the initialization step, store it on the GPU memory, and use it from there. In the CPU, how it's called? Loops were fused aggressively, and in the GPU, in the CUDA code, we fuse kernels in the same way for data locality. And this is another optimization that wasn't in the original CPU code, that we use batched FFTs for multiple codes to make better use of the CPU cores. And that's it for the CUDA. So Sivan will continue.
Okay, so now we dive into the performance results. This is the baseline performance results. So before we started this project, the code would run on desktop computers, desktop CPUs in the base station, sometimes in small form factors, but they're still desktops. So this is a recent Intel i7 CPU and the performance that we achieve on it. The x-axis is the number of patterns or codes that we correlate against. As I said, in searching, which is in blue, it makes sense to look at what happens when you have 100 or 60, even 200 different patterns, different tags that we've not heard for in a while. For tracking, usually it's one, so it doesn't make sense. It's not so interesting what happens when you have two or more. Sometimes two still makes sense. The tag can transmit two different codes, and we may need to know which code it transmits. The y-axis is time scaled per pattern. It's time per pattern, per code, and scaled relative to real time. So if we look at a number like this, so this is roughly 0.1, what it means is that if we process 100 milliseconds of RF, it takes about 10 milliseconds per code. And if we process 256 codes, it means that it took about 2.5 seconds of real time. So 10 milliseconds per code, 10 times faster than real time. If we did this for 256 codes, then it was 25 times slower than real time. So this is how the y-axis scales on all of the graph that I'm going to show next. So this is on one core. Can the batching of the FFTs alone? So the core is single-threaded in our kernels and single-threaded in terms of processing one task at a time. But when we call FFTW, FFTW is multi-core aware, multi-core optimized, and sometimes it can in principle parallelize even one FFT, and we sometimes give it batched FFTs, multiple FFTs concurrently. The answer is it's not doing a particularly good job. So we get some speedups on 2 cores, on 3 cores, on 4 cores. When you use the 5th and 6th cores, it just slows down. And even on 2, 3, and 4 cores, the speedups are not particularly significant, not even a factor of 2. So the code is really single-threaded. The CPU code is single-threaded. The parallelism within FFTW is not particularly useful at these vector sizes. They're not that long. Okay, so the multi-core speedups are very modest. When we move to a same code structure, single-threaded within the signal processing flow, but each kernel is a GPU kernel and uses multiple cores on the GPU, performance improves dramatically. So this is this is performance on a desktop class, a relatively small desktop class GPU. And what we can see is performance improves by about a factor of 10 relative to the CPU code. The ratio between, or the relative performance of searching and tracking changes, but basically we get about a factor of 4 improvement in a factor of 10 improvement in performance from moving from a desktop CPU to a desktop GPU. So that's very useful. When we move from the CPU, not to a desktop GPU, but to an embedded or edge GPU, a low-end NVIDIA GPU, this is the Jetson TX2 GPU, we still get better performance than the desktop CPU. So performance is about 2 or 3 times faster on a low-power edge or embedded GPU than on the desktop relatively high-power CPU. So that's excellent. The Jetson TX2 also has CPU, ARM CPUs. And we use this to try to see whether the improvement is due to the Jetson being just faster clock time. It's not faster, it's really slower, or the move from the CPU architecture to the GPU architecture. And the answer is the performance improvement is due to the GPU architecture. There are 2 different kinds of ARM processors on the Jetson, and you can run the Jetson using different combinations of these ARM CPUs. But using the ARM CPUs, the code is very, very slow. So the same piece of silicon, when you use its CPUs as opposed to each GPU, performance is very, very slow. So the improvement is due to using a GPU. The other thing that you can see on the Jetson is that the GPU on the Jetson is much more power efficient than the Jetson CPUs. So when you run the code on CPUs, which is the energy consumption here scaled as 1, you get some energy consumption. When you move to GPUs, it becomes about 10 times or more energy efficient, less joules per task. So that's sometimes it's not very important, sometimes it's very important. So the high level, and I should say the performance improvements, the throughput, the ability to process more codes per second is important for throughput, for how many tags can be active in the system simultaneously, and the system still being able to copy all of these tags. It's important to have high throughput. The power consumption is not important for a base station like the one I showed before, which is on a cellular tower, because it's connected to AC mains. It's very important for base stations in the Netherlands, for example, which run on wind and solar and battery power. So to conclude, I need to finish. DSP on small RF windows parallelizes great on GPUs. The fact that we use a scheduler eliminates difficulties that people have had with GPUs before when they try to implement hard real-time. This is soft real-time, much easier. We get both high throughput and low power consumption and a good selection of GPUs for users to choose from. If I want to go one level higher, that's my last slide. What we try to find out is whether we can get good performance from simple code. And that's what we did with the GPU. In a system like this, it's being used for many years. It's being used now for 6 years by real users 24/7 over years. Maintenance is important, complexity is important, user education. They need to buy these GPUs, these computers, they need to install the software and so on. So we could also parallelize the scheduler, but it would have added a lot of complexity and it would have been much more difficult to maintain and to educate users. What we've discovered is that keeping the basically single-threaded scheduler and replacing the CPU processing by GPU processing, we get great performance and great power consumption. Okay, we are very happy with the results. I hope that I clarified some of the things that may not have been completely clear in the written paper. We have a revision that's hopefully clear. That's it. Thank you very much for listening.
So thank you, Sivan. So I don't see questions. Yeah, but I have one or two. Yeah?
I have a question, actually.
Yeah, please go ahead.
Okay, so yes, thank you. So really interesting talk. Thank you very much. So when you talk about these filters that you pre-compute, what are their sizes in terms of numbers?
These vectors in tracking, they're about 100,000 elements, 100,000 complex elements. In searching, about 800,000. Mm-hmm. So these are the sizes of these pre-computed vectors.
Right, so there is no other way but FFTs basically, so you cannot consider something like convolution. Okay, great.
In the CPU code, when the filters are very short, we can use either convolution or FFTs, but basically it's faster with the FFTs.
Mm-hmm. Okay, because of the developments in batched convolutions due to deep learning on GPUs, maybe it might be worth it to try to see if keeping it in the same domain might be useful. Okay, thank you.
Yeah, so is there any other question from the audience? Okay, so my question is the results for the performance that you have shown or presented. So do you have the communication time between the host and the GPU? Is the first question.
No, I don't think we measured it separately here. Here, for example, I don't think we measured it, but I think it's relatively minor. I think the communication time, each task starts indeed with copying the actual samples from CPU memory to GPU memory, but then there are like 4 or something like 4 FFTs. I think that these are slower, but it's a good point. We should maybe measure this. There is very little copying back because the data is reduced significantly.
When I profiled it, it was really negligible amount of time took the copy versus the calculations.
Okay, sorry for misleading the audience. I didn't remember that it was profiled.
And the last question, because we don't have too much time, and then so the problem that you found when you try to parallelize with the CPU with a multi-core using multi-threading, so is it related with that the data does not fit with the memory hierarchy? Because you can also use AVX SIMD instructions to exploit data parallelism even in a single core. So my question is, why did you find this difficulty just to reach speed up or to achieve speed up?
We are not completely sure. I would say there is the issue of maintainability of the code. The code is complicated, and sometimes we modify the signal processing to do different things. So having a heavily optimized code it's already optimized in terms of memory accesses. We didn't want to do SIMD computation and so on in our element-wise kernels and in the reductions. We hope that we use FFTW and we compile FFTW to use SIMD instructions and to use OpenMP or pthreads. It still does not provide enough parallelism. And I think the key is what Tal asked. These vectors are fairly short. Even 1 million element vectors is fairly short, and it's a linear vector. The operations are linear. The memory bandwidth dominates, and the improved memory bandwidth on the GPU, in the even global memory on the GPU, is much better than on the CPU. So I think that's the main reason.
Okay. So thank you very much for the presentation and the answers to the questions. So let's go to the next paper and presenter. I think it will be Yaniv.
Yes, it's me, Professor Sousa.
Okay, here. From Paris Sud, right?
Yes.
Yeah, that's RNS. So can you please share the screen to start presenting the?
Yes.
So the work has been done on not only by Yaniv, but also by Stefan and Mark Bubbling.
Yes.
It's about parallelization of the Kappa-Mens algorithms in a spectral clustering chain on CPU, GPU platforms. So the floor is yours, or the Zoom is yours in this case.
Okay, I can start. Okay. Hello, everyone. My name is Yaniv He. And I'm a PhD student at Paris-Saclay University. And I'm very glad to present our work about the parallelization of the K-means algorithm in a spectral clustering chain on CPU, GPU platforms. So first of all, let's look at some introduction to clustering and our research positioning. Clustering is the process of grouping data instances into meaningful subsets in order to reveal the intrinsic structure of data. A good clustering result is supposed to have high intra-cluster similarity and low inter-cluster similarity. And as one of the most important tasks in machine learning and data mining, clustering has numerous applications such as image segmentation and social network analysis.
Sorry, just a minute. Just try to mute the...
Okay.
Okay, please continue.
Okay. K-means is one of the most popular clustering methods. It's based on distance calculation and can efficiently find the convex clusters, but is sensitive to the selection of initial centroids and can be stuck in local minimum solutions. And spectral clustering is another method and has many advantages over K-means. Based on graph theory, it embeds data into the eigenspace of graph Laplacian, and then finally performs the K-means clustering on the embedding representation. Unlike K-means, it can discover both convex and non-convex clusters, and always searches for a global solution. However, spectral clustering has a high computational complexity, which is big O and big N cube, where N is the number of data instances. And this can be a critical issue when dealing with large-scale applications. So here comes the problem. How can we enable spectral clustering for large-scale applications? Basically, there are three main approaches. Some researchers try to reduce the computational complexity through methodological changes. Some apply approximation or summarization techniques so that only a small subset of data is involved in the complex computation. And another way is to accelerate the spectral clustering via parallelization. So we are most interested in this third approach with the use of the GPUs. There are some related works on spectral clustering on GPU, but they often have some of the following restrictions. For example, the data sets are often of small or medium size, and the similarity graph or matrix, as well as the number of clusters, are often assumed to be already given. And in some works, the speed up for eigensolver appears limited, and some other works are dedicated to specific applications. We also found some exploitable CUDA libraries such as cuBLAS, cuSparse, cuSolver, and MAGraph. In cuSolver library, and the cuSolver library contains several eigenvalue solvers and is potential to be used for the calculation of eigenvectors in spectral clustering. And the MAGraph provides an API for spectral clustering. However, it also assumes that the number of clusters as well as the similarity graph in CSR formats are already given. But for a general problem, constructing the similarity graph is necessary and computationally expensive. And in practice, it may also be difficult to know the number of clusters in advance. So our plan is to propose a CPU-GPU-based implementation of spectral clustering with the use of representatives extraction in order to address large data sets. Here's the data flow for our spectral clustering chain. The first step allows to reduce significantly the volume of n-input data instances, extracting KR representatives with the k-means algorithm. And here, each data instance is associated with the nearest representative. Then the KR representatives are transferred from CPU to GPU, and spectral clustering is done on GPU. And here we can see that the spectral clustering is composed of three main steps: the similarity matrix construction, eigenvectors computation, and final k-means clustering. And the clustering result on this for this KR representatives is then transferred from device to host, and we can finally we can obtain the cluster labels of the n data instances according to the attachment relationships in the first step. So we want to parallelize. Our goal is to parallelize the whole spectral clustering chain, and here we can see that we use k-means in two different places, and we need to parallelize the k-means algorithm both on CPU and on GPU. We found some related works about parallel k-means on CPU and on GPU, but they do not consider the issue of numerical accuracy, which may occur in the update phase of the k-means algorithm due to the effect of rounding errors, and this can lead to the poor clustering quality. So the contribution of our current work is the optimized implementations on CPU and GPU for the k-means algorithm with both high performance and numerical accuracy. Now I'm going to show how we optimize the parallel k-means algorithm on CPU and on GPU. First, let's take a look at how k-means algorithm works. The inputs are supposed to be n data instances in dim dimensions, as well as the number of clusters k. And the outputs are supposed to be the cluster labels of n data instances. The first step is to select k initial centroids, either randomly or heuristically. Then we compute the distances between each point to each, from each point to each centroid, and assign each point to its nearest centroid. And we call this step the compute assign routine. Then we update k centroids by calculating the means of data instances that are assigned to the same centroid. And we call this step the UpdateCentroids routine. Then we repeat these two routines until reaching the stopping criterion, which can be either a stable result or a maximum number of iterations. So to parallelize k-means, we use OpenMP on CPU, enable auto-vectorization and minimize cache misses. On GPU, we use CUDA and apply multiple optimization techniques, such as minimizing data transfers, using pinned memory for faster transfers, coalescing memory access, setting optimal sizes for grids and blocks. And in particularly, we use shared memory and dynamic parallelism and multiple streams in the UpdateCentroids routine. In addition, both on CPU and GPU, we minimize data storage and access, and as well as the effect of running errors. We point out that the compute assign routine exhibits a natural parallelism and therefore leads to a straightforward parallel implementation, so will not be detailed here. However, the UpdateCentroids routine appears more difficult to be efficiently parallelized and is a source of running errors, and so I'll present more details for this routine. Floating point numbers can be in single position or in double position, but they all have a finite representation capacity. This can lead to running errors, in particular when adding two numbers of very different magnitudes. In the UpdateCentroids routine, we need to calculate the sum of data instances in each cluster. So when there are a large number of data instances added together one by one naively, there will be an accumulation of running errors. In single position, it can deteriorate the cluster quality. In double position, we can get a satisfying level of accuracy, but the computational cost is higher. So our goal is to preserve the performance of computing in single position and meanwhile minimize the effect of running errors. To do this, we propose a two-step method for the UpdateCentroids routine. So the first step is to split data instances into a certain number of packages of similar size and calculate the sum within each package. The second step is simply to compute all the local sums of all packages, and compute the sum of all packages to get the global sum. So by choosing an appropriate number of packages, we avoid adding numbers of significantly different magnitudes and therefore obtain satisfactory numerical accuracy in single position. So how to efficiently parallelize this two-step method on CPU and GPU? Here's our CPU code for the UpdateCentroids routine. We use both private and reduction clauses in OpenMP directive to parallelize the outer loop of the two-step reduction. And the inner loops access contiguous array indexes and avoid divergences so they can benefit from auto-vectorization engaged with the O3 compilation flag. On GPU, by using dynamic parallelism, the host code is simplified into just 2 parent kernel launches. And each parent grid is small and contains the number of threads equal to the number of streams, which means we use 1 thread per stream. And the device code for parent kernel of step 1 is like this. Each thread processes several packages on its own stream, and and each thread launches 1 child grid per package. And child grids launched on different streams run concurrently. And this strategy allows to optimize the GPU usage independently of the number and size of packages. And finally, the CUDA stream destroy ensures that the stream will not be used to launch other threads, where a parent thread will only end until all of its child threads complete. So the device code for the child kernel of step 1 is like this. And this is the first part, some preparation work from before operating on the shared memory tables, including the declaration of shared memory tables, index computations, and load data into shared memory tables, and synchronization of threads. And this is the second part. So by using shared memory, threads in the same block calculate the local sum by block size at first. Then all the local sums are added together via a few atomic add operations to get the global sum. And in this way, the expensive atomic add operations are performed by every block instead of every thread, and therefore are reduced significantly. A similar strategy is used to implement the step 2 of the UpdateCentroids, so we omitted it here. Let's move to the experimental evaluation. Our testbed is a CPU plus GPU server. The CPU contains 2 10-core Intel processors, which means 40 logic cores in total. And the GPU is a RTX 2080 Ti. Our CPU code is compiled with GCC, and our GPU code uses a separate compilation mode for dynamic parallelism. As benchmark, we use a synthetic data set created on our own. It contains 50 million data instances, 4 dimensions, and are distributed evenly in 4 convex clusters. This data set has been created in a way that the K-means algorithm would not be trapped in local minimal solutions. And the benchmark for numerical error here is of order 10 power minus 4. And in addition, we iterate the algorithm until all the clusters have become absolutely stable. So here's the results for the K-means clustering on CPU. We observed that using a certain number of packages reduces the numerical error in single position. And in our case, using 100 packages is enough to achieve the same numerical accuracy as in double position. And it is proved that using single position instead of double position decreases the elapsed time. Here's the results on GPU. Again, using packages reduces the effect of rounding errors. But this reduction is, on GPU, this reduction is enhanced by using shared memory since it allows initial local reductions. The UpdateCentroids routine on GPU is the most time-consuming, while the compute assign routine represents only a small proportion of the time of the runtime. The Centroids initialization and most of data transfers are performed only one time, so their impact on the whole runtime decreases with the number of iterations. And the overhead time of some regular transpositions of small data appears negligible. In our GPU optimization, in our GPU implementation, we also set the optimal configuration for grids and blocks. And here's an example of how block size and block configuration affects the performance. Here, each package is processed by BSX P times dim threads. And it is clear that in this case, the optimal choice for BSXP is 32. And this figure demonstrates the impact of GPU optimization on the running time of UpdateCentroids. So compared to the naive implementation with many atomic add operations, using shared memory reduces significantly the execution time. The dynamic parallelism also improves the performance in the case of 100 packages and 1,000 packages. However, it degrades the performance for 10,000 packages. This is because the GPU hardware resources are not fully concurrently exploited when there is a large number of small packages to be processed on the default stream. Therefore, introducing multiple streams contributes to the concurrent use of hardware resources and reduces the execution time. Finally, we found that the combined use of shared memory, dynamic parallelism, and multiple streams achieves very good performance for a general number of packages. So here display the speedups for the two routines and the resulting loop of the K-means algorithm. For the K-means loop, the best speedup compares to the sequential implementation is almost 10 times on CPU with 40 threads, and almost 50 times on GPU which is 5 times faster than on CPU with 40 threads. For the compute assign routine, we achieve much higher speedups, around 300 times on GPU than on CPU. However, the speedups for the UpdateCentroids routine are similar on CPU and GPU. So in conclusion, we have proposed parallel implementations on CPU and on GPU for the K-means algorithm. They serve as some parts of the computational chain for spectral clustering. And we have also addressed the numerical accuracy issue with single position by a two-step reduction method. This numerical accuracy issue may occur in the phase of updating centroids due to the effect of rounding errors. And for the GPU implementation, we maximize our performance with dynamic parallelism, shared memory, and streams. And experiments on our dataset show both numerical accuracy and parallelization efficiency. As future work, we plan to evaluate our implementations on real-world datasets and also compare our implementations with other existing ones. So thanks for your listening. Do you have any questions?
So thank you. Are there any questions from the audience? Let me just see if someone raised the hand. Okay. So my first question was exactly so in the final statement in the conclusions, as you said. So I guess there are a lot of work on implementing Kaplan's algorithm, which is quite important in GPUs. So do you have an idea how do you compare in practice your proposal with the others?
Compare our implementations with
in terms
others.
of evaluation, yeah. In terms of results, experimental results.
Performance and results.
Yeah.
Yes. In fact, it's our plans to do it as future work to compare it with the other existing implementations.
So you just as it can be expected, you just, because you have some serial processing in this type of algorithms that I know. So for some parts of the processing, so you are able to speed up in the GPU a lot, but in the other parts, so did you try to use an heterogeneous systems that part of the algorithm is running on the CPU and then concurrently you have other parts running on the GPU and then cooperate or collaborate just to speed up the overall processing time?
We believe that we should minimize the data transfers between CPU and GPU. So we keep the whole program running, the whole program of K-means run on the GPU. And we also achieve the similar speedups on CPU. So we think that it is not worth to move the UpdateCentroids routine and on the CPU.
Okay, but if you change the system with a communication bus that is faster, like you have in, for instance, when you have a GPU communication, you can think on that, right?
Yeah.
So, okay, so Gwalin, thank you very much for your presentation.
Thank you very much.
For your participation in Heteropar 2020. So I will go to the next paper. So, sorry, something. Okay. So it will be entitled High Performance Portable Solver for Triagonal to Applet System of Linear Equations. So I think Beata Dimitruk.
Yes, can you hear me?
Here to present. Yeah, perfect.
Okay.
So please go ahead, so you can start presenting.
Thank you. Hello, everyone. My name is Beata Dmitruk, and I'm presenting Maria Curie-Skłodowska University in Lublin. I am co-author of the paper called High Performance Portable Solver for Tridiagonal Applet Systems. And let us consider tridiagonal applet systems of linear equation. That is a system with the matrix of the coefficients consists of 3 diagonals, and on each diagonal we have the same elements. For the sake of simplicity, we can assume that the size of the problem is the power of 2. Such systems appears in numerical algorithms for solving boundary value problems for ordinary and partial differential equations, piecewise cubic interpolation, and spline algorithms. The methods of multi-grid line relaxation, alternating direction implicit, and cycling reduction for solving elliptic equation, and of course in others. There are several methods for solving such systems. Basic idea comes from Roger, who proposed methods for solving symmetric tridiagonal applet system using a simple LU decomposition for a system with almost applet structure together with Sherman-Morrison's formula. This approach has been modified to obtain new solvers for possible parallel execution in Gary and Vidal. A simple vectorized but non-parallel algorithm was proposed in Chang and Yan. A simple vectorized different approach was proposed by McNally et al., who developed a scalable communication-less algorithm. It finds an approximation of the exact solution of the systems with the given acceptable tolerance level, and does not utilize vectorization explicitly. Terkov proposed a highly scalable parallel algorithm for solving tridiagonal applet system with multiple right-hand sides. We propose an OpenMP algorithm for solving such systems. To find the solution to a system Tx equal to F, we can follow the approach presented in Chang and decompose matrix T into the sum of a product of a lower and an upper triangular matrix, and the matrix consists of only one non-zero element. We can calculate parameters alpha and beta from the given formulas. Using this decomposition, we can rewrite the equation as follows. We also denote as a vectors u and v. Then the solution to consider system can be found using presented formula. Note that in order to apply this formula, we need to find two denoted before vectors, v and u. We do it by solving two systems of linear equations with the same coefficients matrix, that is L times R. these systems are L times R times U equal to E0 and L times R times V equal to F. This presented formula will be the last step of our algorithm. The solution to a system of linear equation R times Y equal to D can be found using a simple sequential algorithm based on the to this following recurrence relations. This simple algorithm can be efficient only for small values of n, of the size of the problem, because it does not utilize the underlying hardware of modern processors, namely multiple cores and vector units. In order to develop an efficient algorithm for solving presented system that could be performed parallel and to provide its portable implementation for both CPU and GPU architectures, we apply the divide and conquer implementation using OpenACC. Let us assume that the size of the problem is equal to R times S, where both R and S is greater than 1. First of all, we arrange entries of L into blocks. Here we show an example where R and S is equal to 3. Of course, in our computation, the size will be the power of 2. Then we obtain the following bidiagonal block matrix. This matrix consists of bidiagonal matrices LS and one element matrix B, one non-zero element B. Then the lower bidiagonal system of linear equation L times Z equal to F can be written in the following recursive form. This formula has a lot of potential in parallelism. Just after all vectors here on the left side have been found, we can apply this formula to find all vectors Zi one by one. It is clear that to find all Zi, we need the last entry of previously Zi minus 1. Thus, one thread should find the last entries of all vectors Zi, and then S minus 1 entries, first entries, can be found in parallel without the need for synchronization. Similar situations is in the case of upper bidiagonal system R times Y equal to Z, and we do the same what we do with the matrix L. We do the same with the matrix R. And we have the similar situation as previously. So first we need to find the left side of the given formula, and then we need to know first, in this case, first entries of all vectors yi to find all other entries simultaneously without the need for synchronization. column-wise format is the most natural because there is no need to do any data transfer, often choosing specific values of the parameters R and S. Unfortunately, this format does not allow to use coalesced memory access of global memory during some steps of our algorithm. Therefore, we consider both column-wise and row-wise storage formats considered by us two-dimensional double precision arrays. We also consider two forms of format conversion. First one, presented here, is a simple conversion. The figures show us simple parallel loops that can be used to convert between column-wise storage format and row-wise storage format. Such conversion between formats can significantly reduce the overall performance because of non-coalesced memory access. In order to improve the performance of the implementation, let us consider a more sophisticated method for conversion between column-wise and row-wise storage formats uses cache memory. Each gang of B-size threads is responsible for reading a block of VL times B-size elements from the array stored column-wise using coalesced memory access and writing it to cache memory. Then such a block is moved to a new array stored row-wise. Here we present an implementation of a given conversion with device cache memory usage. The algorithm for solving presented system can be easily implemented using OpenACC. Here we present a first step of algorithm that is finding a solution for a first part for lower triangular matrix. Steps presented here, A1, A, and A3, can be vectorized and parallelized using parallel loop construct. It means that the execution of the independent loops will be distributed among gangs that work in SIMD mode, utilizing available hardware. The step A2 is sequential and should be done by a single gang. On the left, we show our OpenACC implementation of the given steps, A1, A2, and A3, using the column-wise storage format for the matrix X, stored as a double precision array. And on the right, we show the algorithm for a row-wise storage format. All experiments have been carried out on 4 different target architectures, which are modern accelerated systems, allowing OpenACC and OpenMP programming models. This is multicore, Kepler, Volta, and Turing. We achieved our results by solving the system of linear equation which arise for second order ordinary differential equation of the given form. We have tested 3 versions of our parallel implementation. The first one uses column-wise storage. The next 2 implementations rely on row-wise storage. The first one using the simple conversion between data and the more sophisticated method that utilize device cache memory. The parallel algorithm have been tested for various parameters of the size of the problem and various values of the parameter R and of course S. Let us present the results. The first one is multicore. We can observe that column-wise storage is the best for multicore, and in this case, there is no need to perform any conversion to row-wise storage. On this architecture, we have also tested the algorithm based on sequential formulas and the simple parallelization of the final formula. We can notice that column-wise storage is the best for CPU-based architecture, and it achieves very good speed up to 9.7 over the simple method. Here we have results for Kepler. For this architecture, row-wise storage is better than the column-wise, but the best results achieves row-wise with cache memory usage. Because of global memory limitation, in this case, and later in case of Turing, the biggest considered problem size is 2 to the power of 28. We can observe that the use of cache memory allows to speed up conversion between considered storage formats, especially on Kepler. The next one is Volta. Here we can observe that simple conversion gives better result only for a certain point, which is here 2 to the power of 24. And for the biggest considered system, row-wise with cache memory usage is significantly better than the other ones. This table also shows the order of relative error achieved when solving presented before system of linear equation arise for second order ordinary differential equation. Let us observe that the relative error of the solution is acceptable. However, its numerical properties, especially stability, should be more studied. The last one is Turing. Here we can observe that simple conversion give better results only for a certain point, which is similar to the results achieved on Volta. But like previously, for the biggest considered system, the results are the best for the row-wise with cache memory usage. We also have observed that for GPU's architectures, the best performance is when parameter R is the approximately the square root of the size of the problem. The same approach can be used for different kinds of matrices. Here we present some matrices which are obtained in solving other kinds of boundary value problems. We have presented the new portable OpenACC implementation on the solver for tridiagonal template system of linear equation. In our numerical experiments, we show that column-wise storage is the best for CPU-based architectures, and it achieves very good speed up to 9.7 over the simple method. The implementation using row-wise storage achieves much better performance than the version using column-wise, and the use of cache memory allows to achieve the best performance on consider GPUs. And all consider GPUs outperform the CPU-based system. It should be pointed out that our implementation can be also modified to utilize both CPU and GPU cores. In such case, each S times R matrix can be split into two separate blocks. The first one can be allocated in the host memory and the other one in the device memory. The host block should be stored column-wise, while the device block row-wise. In order to program computation, we should use OpenMP to utilize CPU cores, and OpenACC constructs to utilize GPU cores. Computation on GPU should be spawned using the OpenACC parallel constructs with the async clause. To synchronize computation on CPU and GPU, and to exchange data between host and device memories, we can use the OpenACC wait and update constructs. The experiments have shown that our prototype hybrid implementation on Kepler is about 10% faster than the basic implementation using GPU. The values of parameters R1 and R2 should be chosen to ensure a balance between CPU and GPU computing. For example, for the biggest considered program on Kepler, which is 2 to the power of 28, and the best parameter R, that is 2 to the power of 14, the value of R1 should be 2 to the power of 11, and of course R2 should be equal to R minus R1. In the final version of the paper, we will present more comprehensive results. Thank you for your attention.
Thank you, Vieta, for presenting us this interesting solver for triadiagonal template systems. So there is any question from the audience? Is there any question? Okay, so you tried. I think it's also simpler to use, or you use OpenACC for this work. So did you try to use other tools, programming tools, like for instance CUDA or?
Not yet, but we strongly consider using it to perform other kind of the same approach.
Yeah, and by curiosity, so you use the row-wise organization with cache is the one that you achieve the best results in GPU? Is it easy?
For the biggest consider system, it is the best.
So is it difficult to just to give the pragmas to the OpenACC just to use the caches, or?
Yes, so transformation between data, I don't know if there is, you can see my presentation still. Yeah. The simple conversion is presented here, and like we see, that is two basic loops, and with the cache memory usage here, the implementation look like this. This is from column-wise to row-wise, and the same approach will be to come back with the when we get the results.
Okay, so it's not difficult to use the cache. You do the transposition in the easy way also.
Yes, maybe difficult will be the correct indexes writing.
Yeah, that's why my question. So, and the last question. So, do you plan to have an automatic method to choose the optimal values for R1 and R2 when you have this hybrid solution?
This will be the best approach if we can handle with the automatic choosing these values. This will be the best what we can do.
Okay. So thank you very much for the quite interesting presentation and work.
And thank you.
So, and with this last presentation, so we will close this 2020 edition of the Heteropar. So on behalf of the steering committee, I would like to thank a lot the organization. So it was a quite difficult year for organizing conference and workshops. So Roman, thank you very much. So and also I think you have the support of also the organizers of Heteropar. So if you want to say last words, so please go ahead.
Of course, of course. So in this way, we are at the end of this workshop. All points of this workshops were implemented. Fortunately, everything was, I think, okay. Yes, this year is very difficult. This year was very difficult because even the decision about implementing, realizing these workshops was very late, as a matter of fact. We had to wait for the decision of the Heteropar organizing committee to do this, to make this workshop or not. But we insisted all, especially with the help of Alexei, but also other people, to have this workshop. And this workshop is the largest among all workshops of Heteropar. So I am happy that we were able still to implement, to realize this workshop. It needed a lot of work of many people, also from the program committee, from steering committee, me as well. So I would like to express my gratitude to all participants, to all presenting authors, to all members of the steering of program committee and steering committee as well. And now we have to finish our work by submitting this camera-ready version of papers, also by preparing this special issue. I hope, maybe it's very difficult to have this hope that the next year you will have possibility to implement, to realize a physical conference. It's not obvious, completely not obvious, because the situation is still not so good. But thank you. I would like to express my great thanks to everybody who participated in preparing and implementing this workshop.
So thank you very much, Roman. So a last word, just to say that the next edition of Heteropar will be in Lisbon next year.
Oh.
So you are all invited to submit papers to Heteropar.
Yeah.
We hope to have a presential conference, and so I would like to invite you all to submit the papers to the workshop, and also visit Portugal next year by the end of August, because the weather is good and also the country is a good one, so you can. I think it will be. I hope to organize a nice conference and workshop. So please submit your work to the Heteropar 2021 edition.
Yes, so it will be. It is a very good finish. Yes, because symbolic finish. The chair is the main man of the next Europar conference. Yes. Thank you.
So thank you very much.
Thank you very much.
Thank you, everybody. Bye-bye. Thank you, Roman.
Thank you.
Thank you, the organizers.
Thank you for organizing it.
Physical. Unfortunately, it's not physical conference. Unfortunately, but
Next time.
next time,
year.
yes, we hope. We hope for the next time.
Yes.
So Maciej, do you want to say something? You just connect the...
Okay, no, just wanted to say thank you.
Okay. Okay, so bye-bye.
Bye bye.
Bye-bye.
Great job. Thank you.